Hello everyone. In this video, we are going to talk about the section 9.2, which is about partial derivatives. For the first example or problem here, the temperature, which is T, capital T in degrees Celsius, at a location in the northern hemisphere depends on the longitude X and latitude Y and time T. So we can have a triplet here, X, Y, Z, and let's X denote the longitude, where increasing X means moving east and increasing Y means moving north. Now, the question is, what are the meanings of the partial derivatives? Partial derivative of t with respect to x, partial derivative of t with respect to y, and partial derivative of t with respect to z. Sorry, t. It should be t here. So we know that partial derivatives are all about rates of change, but in different contexts. In here, partial derivative of capital T with respect to x is the rate at which the temperature changes with longitude, because x is representing longitude, while latitude and the time are fixed. So when we are finding the rate of change with respect to x, which is longitude here, it means that other variables like y, which is latitude, and t, which is time, will be fixed. Now, what is the meaning of partial derivative of t with respect to y? That would be the rate at which the temperature, capital T, changes with latitude while longitude and time are fixed. Same for the last one. Partial derivative of t with respect to t, lowercase t representing time, means the rate at which the temperature changes over time, while longitude and latitude are fixed. Part B of the same question, it says that Honolulu has longitude 158 degrees Celsius and latitude 21 degree north. So this one here should be west, not Celsius, because longitude is not about degree temperature. Okay, so again, it has the longitude 158 degree west and latitude 25 degree north. Suppose that at 9 o'clock a.m. on January 1st, the wind is blowing hot air to the northeast. So northeast here, if we want to draw the coordinates here, if this one is north and this is east, west, and south, somewhere here will be northern east. And it says that the wind is blowing hot air to the northeast. So the air to the west here and south is warm. So these are warm. This is warm. And the air to the north and east is cooler. So these are cool here. And we know that this can be x-axis, this one can be y-axis. And the question is, what do you expect for f sub x, which means first derivative with respect to x, derivative with respect to y, and derivative with respect to t? We know that these are rates of change on using different points. So for this specific point, the first derivative with respect to x at the point 1, 5, 8, 21, and 9, since when x is increasing based on the question, let's see the question again here. According to the question, it says that when x is increasing, it means moving east. So in this point, if we want to change x here, it means that it's moving east and that it would be cooler. So from a warmer place to a cooler place, the difference will be a negative one because the second one minus the first one will be a negative. So what about moving north, which is first derivative with respect to y of the same point? With the same idea, that would be negative because we're starting from a warm place, ending cooler place. And for the last one, which is derivative with respect to t of the same point, it will be positive because when time passes, the point gets warmer. And the reason for that is based on the question, warm wind is blowing. When the warm wind is blowing, so the temperature will be higher and the rate of change here would be a positive number. Let's do number 2. It's a contour map and is given for a function like f. Use it to estimate first derivative of f with respect to x for the point 2 and 1, and also first derivative of f with respect to y for the same point. So first derivative of f with respect to x for the point 2 and 1. Let's find this point. Let me use another color. Okay. So 2 and 1 is somewhere here. This is the point that we're talking about. So the rate of change here, when x changes in the x direction, can be the points a little bit before and a little bit after that. So if we go before, that would be this point here. And this point is approximately, let's say 1.2 and 1. And f of this point is 8 because it's located on this line here. Okay, we need another point. Let's move the other way. If we move this way, we will have a point here, maybe 2.8 and 1. And the f of this point, since it is located on the curve with 12 as the value, will be 12. So what was the f of 2 and 1? That is 10, because this point is located on the line with 10 as the value. Now, having all these points, 3 of them, if we find the rate when the changes between these 2 points, the rate of change will be the changes of y values here, which is the second one minus the first one, 8 minus 10, over the part that changes here is x. So the second one is 1.2 minus the first one, which is 2. It will be negative 2 over negative 0.8, and this one is 2.5. But let's say this is number 3. So the rate of change between number 1 and number 2. But what is the rate of change between number 2 and 3? For this, it will be 12 minus 10 over the part that changes, which is 2.8 minus 2. So again, it will be 2 over 0.8, which is 2.5. Comparing these, we may find other points too. Comparing these, we can say that f of x of 2 and 1 will be 2.5. Same process when you want to find f with derivative of f with respect to y. Let's pick other numbers here. Now this time, the point 2 and 1, which was somewhere here, we're going to move it along y-axis. So basically we had 2 and 1, and f of this point is 10. But what if it is moved one of these lines up? It will be f of the same x value, but the y value changes, it's less than 2, let's say 1.9, and that is 8. If we move down, the point that you get here has the x value the same as the main one, and the other one can be a little bit above 0, maybe 0.2. And the answer for this is 12 because it is located on this line. And the rate of change for, let's say, 1, 2, 3, between 1 and 2 here is 8 minus 10 over 1.9 minus 1, which is approximately negative 2.22. And the rate of change for the point 1 and 3 is 12 minus 10 over 0.2 minus 1, which is approximately negative 2.5. In this case, that these rates of change are not the same, you can find the average or approximately a point between these. And that can be a number like 2.3 here. You may add them up, divide by 2, and get a number here, but this is a negative. Let's do number 3. Find the first derivative of the following functions. So when it says first derivatives, it means that you're going to find first derivative with respect to x of x and t, also first derivative with respect to y of x and t. For the first one, since it is with respect to x, pick the part that has x in it. Find the derivative. It's chain rule for single variable functions, and that would be pi times negative sine of pi x. And then multiple the rest of it. So this is the fastest way. For the second part, with respect to y, we don't have y here, so it will be with respect to t. Pick the part that has t in it, which is this part. So the derivative of this part is negative e to the power negative t times whatever is left. For part B, we can find derivative of f, which is z here, with respect to x. So we have only one part and it has x in it. it will be the power, it's chain rule, times the derivative of the inside times itself to the power 1 less. And then you can write it as 2x plus 3y to the power 9. When we find the partial derivative of z with respect to y, that would be the same process, but this time 10 times the derivative of the inside times 2x plus 3y to the power 9, and it will be 30 times 2x plus 30y to the power 9 here. Next part. In here, when we are going to find the first derivative with respect to r of r and s, we have two different parts here, and both of them has r in them. So it means that you're going to use product rule. For product rule, you can copy the first one, derivative of the second one with respect to r, which will be 2r over r squared plus s squared, plus copy the second one with respect and derivative of the first one with respect to r, which is 1. And finding the derivative with respect to s for r and s will be same thing, but with respect to s. So copy the first one, derivative of the second one with respect to s, and copy the second one, derivative of the first one with respect to s. The first one is r and it doesn't have any s in it, so this will be 0. So actually you don't have this part. Next one, derivative of f with respect to x will be, so this function here is arctan or tan inverse. So if it was just tan x, tan inverse of x, the derivative was 1 over 1 plus x squared. Since in here we don't have just x and we have an expression, we have to multiply whatever it is by the derivative of that thing with respect to the variable that we are talking about. So in here, since the variable is x, it will be the derivative of inside with respect to x, which is square root of t times 1 over 1 plus whatever you have, which is x square root of t to the power 2, and you can simplify this as square root of t over 1 plus x squared times t. Same idea when you're going to find f with derivative of f with respect to t. That would be the derivative of inside, which is x square root of t, this time with respect to t. So we know that the derivative of square root of t itself is 1 over 2 square root of t. And we would multiply this by x. So this is the derivative of inside, which I will write it here, times 1 over 1 plus whatever you have as the inside to the power 2. And you can simplify this as x over 2 square root of t times 1 plus x squared times t here. Next one is part E, which looks like to be an integral, which is actually an integral, but we're going to find the derivative of that. Based on the first fundamental theorem of calculus that you have read previous semester, that would be f of x, x and y, the derivative with respect to x. It means that you're finding the derivative with respect to x of this integral. And that theorem says that you're going to change the variable to whatever you have here, which is cosine of x squared times the derivative of whatever you have here, which is 1, and you would have cosine of x squared here. For f with respect to y of x and y, we have to change the boundaries here. So we're going to write negative because we're going to change them here. And this time the derivative with respect to y. And based on the theorem, when you're finding the derivative based on y, that would be here. For the first one, it was with respect to x, which was here. And since for the first one, we are finding the derivative with respect to x, it means that y here is just a number. If you remember, that theorem says for all integrals from a number to a variable. And that works here because we are only talking about one variable at a time. So cosine of t squared dt. So we keep the negative here, and it will be cosine of y squared times the derivative of whatever you have here, which is 1. So the answer will be negative cosine of x squared. Last one in this question, f of x and y is x to the power y. So when we are finding the derivative with respect to x of x and y, that means that you have something like x squared, x to the power 5, because x would be a variable, y, which is the power here, is a number. And we know how to find these. So that would be y as a number, x to the power 1 less. But when you're finding f with respect to y of the same formula here, the same expression here, that means the same as if you're finding the derivative of 2 to the power x or 5 to the power x, because in this case, x is a number and the power is a variable. So in here, based on the laws of derivative of exponential functions, that would be x to the power y ln of x. In general, if it is x to the power, a to the power x, which a is a number, and we're finding the derivative, that would be a copy of this times ln of the base. Number 4 is asking about the derivative with respect to x of this function, but this time we would plug in 3 for x and 4 for y. So the derivative with respect of x for the function of two variables, x and y, and in here we're going to find the derivative with respect to x. That would be the derivative of the inside times derivative of the function, which is 1 over x plus x squared plus y squared. Because if it was only ln of x, the derivative would be 1 over x. Based on this, we write 1 over whatever we have as the derivative. And since it's using chain rule, we're going to multiply this by the derivative of the inside, which will be 1 plus 2x over 2 square root of x squared plus y squared times 1 over x plus square root of x squared plus y squared. And we're going to plug in 3 and 4, 3 for x, y for 4, and the answer would be 1 over 5. Question number 5 is about finding implicit differentiation. For finding implicit differentiation, I would write it here. We are going to write the step-by-step of the derivative. And for the first step, it would be the derivative with respect to x of x squared plus y squared plus z squared. And for the right side, it will be the derivative with respect to x of whatever we have here. But since we are only considering x as the variable, it will be easier if we write it as 3y times xz, or whatever you would like to write that. So left part, since we're finding the derivative with respect to x, it will be 2x plus 0 plus 0. No, not 0 here, because the difference is in here, we know that z is a function with respect to x based on this. So in order to find that, since it is implicit differentiation, we would write the derivative of z, but we don't forget that z is a function with respect to x. So we would consider that here. For the right side, it can be a product rule. For the product rule, when you find the derivative, you can write 3 times y as the coefficient. And for this part, it's a product rule because x is the variable, and we know that z is a variable which is dependent on x. So we should consider both of them. So copy the first one, derivative of the second one, plus copy the second one and derivative of the first one. Makes it 3xy plus 3xy times the derivative of z with respect to x. Now, we're going to solve this for derivative of z with respect to x. So finding both of them means that you would move them to one side, either the right side or the left side. So I would say that I'm going to move them to the left side. So 2z times derivative of z over derivative of x minus 3xy derivative of z over derivative of x is going to be 3xz. This is z here. Okay, this is yz. Minus 2x. And from this, we can factor out whatever we're going to find, which is derivative of z with respect to x. We're left with 2z minus 3 xy equals 3yz minus 2x. And from here, derivative of z over x, which means with respect to x, will be equal to 3yz minus 2x over 2z minus 3xy. Number 6. So this model is given to us and it's asking about the derivative of s with respect to w. It means that we are going to find f sub w of the W and H. So we choose the part that has W in it, which is this part. This is W to the power of a number, something like x squared. In order to find this, that's the usual formula of power function. And we would keep all other numbers besides that. So we would keep 0, 1, 0, 9, 1 here. We would have h to the power 0.725. And for finding derivative of w to the power 0.425, it will be 0.425 times times w to the power 1 less than whatever we have here. It means 0.425 minus 1, which is 0.725. And that would be calculated for the point 160 as the first variable, which is w, and 70 for h. Using calculator, we would get approximately 0.545 feet squared per pound. And interpretation would be, since it is a partial derivative, that would be rate of change. So this is the rate at which body surface area increases with respect to the way when an individual weighs 160 pounds and has the height of 70 inches. Number 7. Verify that the conclusion of Claire's theorem holds here for this function. So having this function, we're going to find the first derivative with respect to x. Since it is tan of something, the derivative would be secant square of that thing. And in here we have 2x plus 3y, so we should multiply that by the derivative of the inside, which is 2 when you take derivative with respect to x. Secant squared of 2x plus 3y. And from this, we're going to find the derivative with respect to y as the second derivative. So in here, we should consider the coefficient, the power, and the derivative of the inside, which is 2. No, which is 3, because we're going to find the derivative with respect to y. And the function of 2x plus 3y. But we need to multiply this by the derivative of secant. So we're looking at this function as secant of something to the power 2. So we keep 2, we put the power, we put the derivative of the whatever we have in the box, which is 3 secant squared. And now so for the derivative of secant squared, we set the derivative of secant first, which is secant tangent of 2x plus 3y, and multiply this by the box itself with the power 1 less, which is secant of 2x plus 3y. And after simplification, that would be 12 secant squared of 2x plus 3y times tan of 2x plus 3y. Another part is finding u with respect to y and then x. So starting with u with respect to y, that would be the derivative of the inside, which is 3, and secant squared of whatever we have. 2x plus 3y. And then from this, we are going to find the derivative with respect to x. So again, we have secant of something squared. We should write the coefficient. We should write the power. And now we should find the derivative of the inside the box, which is 2, not 2. So again, it will be the coefficient, it will be the power, and it will be the derivative of the inside with respect to x. This is why we write 2 here. And the derivative is secant of whatever we have, tangent of whatever we have, times the box with a power 1 less, which is secant of 2x plus 3y. So altogether, it will be 12 secant squared of 2x plus 3y times tan of 2x plus 3y, which is the same as the previous one. So this is satisfied and the theorem holds here. Number 8 is about finding the partial derivatives. So for finding the partial derivative here, which is f with respect to x, then y, then z. So f with respect to x of x and y and z will be the overall function here is a cosine. So it is cosine of something. So it means that when we are finding the derivative with respect to x, we should find the derivative of inside with respect to x. And the derivative of cosine is negative sine of whatever you have here. And from here, we're going to find the derivative with respect to y. So we would keep negative 4 here. We're going to multiply this by the derivative of inside with respect to y, which is 3. And we're going to find the derivative of sine, which is cosine of whatever we have here. And for the last part, okay, we can simplify this first. For the last part, it will be taking derivative with respect to z of the function that we have as the derivative for x and then y. So we keep the coefficient, we find the derivative of inside with respect to z, which is 2, and the derivative of cosine is negative sine of whatever you have here. And we can simplify this as 24 sine of 4x plus 3y plus 2z.